Hi, everyone. So last time we went over the conjunction rules for probability and the negation rule, and this time we're going to hit up the disjunction rules and the definition of conditional probabilities. So this is our second to the last lecture. So next week I will record one more lecture, and then you'll be left to complete the remaining quizzes. There will be 10 quizzes total, including those that you had to take prior to everything happening. And so once you complete those quizzes, then you'll, as long as you complete everything, you've been given another path towards getting a 4.0. And if you complete them all to my satisfaction, then you'll be able to get that. So let's just go over real quick what the past rules were so far, just to make sure that we review things and that you see, importantly, the contrast between the conjunction rules and the disjunction rules. So recall that there were two conjunction rules: the restricted conjunction rules and the general conjunction rules. The restricted conjunction rule just says that the probability of a conjunction is equal to the product of that conjunction, of each of the individual events in the conjunction. So the probability of A and B is equal to the probability of A multiplied by the probability of B. The general conjunction rule says that the probability of the conjunction is equal to the product of the probability of the event A multiplied by the probability of B, given that A has already occurred. So recall that when you apply these rules, they have to apply to very different circumstances, and the circumstances that we're concerned with are those circumstances where the events in question are dependent or independent of each other. If the first event has no effect on the second one, then we would call those events independent, and we would apply the restricted conjunction rule. If the events do influence each other, or at least if one influences the other, then we call the events dependent, and we apply the general conjunction rule. So recall that the examples we used to talk about the general conjunction rule were examples like drawing a card from a deck and then throwing the card out and then drawing another card. And so because the population of cards has been influenced by that first action, it should have, unless the population is like infinitely large or something like that, it should have an influence on the probabilities of subsequent events happening. And so we want to be able to capture with accuracy those kinds of situations. Then we have to deploy the general conjunction rule. Okay, so the general conjunction rule is something to remember. Remember that it is concerned explicitly with that ampersand, the and connective. The disjunction rules look a little different. So let's look at what they say. So we have this V here. Recall that according to our notation, the little V symbol means or, right? So in this case, then we have the restricted disjunction rule. The restricted disjunction rule says that the probability of A or B is equal to the sum of the probability of A and the probability of B. So the idea here is that if you want to say, well, what's the probability of getting a 1 or a 6 in the single roll of a die, then what you would do is you would say, well, let's take the probability of getting the 1 and then the probability of getting the 6 and then sum those together. And once you take the sum, you have the probability of one or the other happening. Okay, and so just like the conjunction rules, these have specific contexts of application, and you need to be careful about what's going on in the problem so that you know exactly when it is that you should apply the rule. So for example, the restricted disjunction rule says that the rule applies when the events that we're talking about are mutually exclusive. So what does that mean? Mutually exclusive here just means that the events cannot happen together. That is, they're inconsistent, right? So think about this in terms of the flip of a coin. If we ask what the probability is of flipping heads or tails, well, we know that in virtue of getting heads as a result, we have not gotten tails. And in virtue of getting tails, we have not gotten heads. And there is no possible set of circumstances where we would say that we have both outcomes. That is, the coin has landed heads and tails. So in the situation where, say, I ask you what the probability is of a coin landing a certain way, as long as you know that the coin can't land on both sides at the same time, you would have to infer that the restricted disjunction rule applies to that problem, because we're dealing with mutually exclusive possibilities. And so that's the thing you want to think about, is whether the events in question are mutually exclusive. So now in the next case, there are situations where events are not mutually exclusive, and we want to be able to think about exactly how those events might, how we might calculate the probabilities for those events. So the general disjunction rule says that the probability of a disjunction, the probability of A or B, is equal to the probability of A plus the probability of B minus the probability of A and B. And so this one might look a little more confusing. And so to understand why we have to subtract the probability of A and B, you want to be able to think about this graphically. The basic idea ends up being that if two events are not mutually exclusive and can happen at the same time, then if you take the probability of A and you take the probability of B, and you add them together, you're double counting actually, because there's going to be a space between A and B where both A is happening and B is happening. And if you add all of A and add all of B, then you're also adding that overlap. And so you're going to count some of the elements in the population twice. And so to try to account for that, we subtract the overlap of the probability of A and B. Okay, so these are the same kinds of rules that you've seen before in a certain sense, right? You've seen the conjunction rules. There's a restricted and general version. There's also a restricted and general version of the disjunction rules, and you want to be able to think about what the conditions are under which they would apply, and you want to think about, well, what am I dealing with here? When I roll a die, does it coming up on one side exclude all of the other possibilities? If yes, then you're dealing with mutual exclusivity. Let's say that I want to, if I want to know, I have a big urn filled with plastic balls, and I say, okay, what's the problem? And this is a silly example, but it's something to think about. What's the probability that I draw something that is red? Say the urn contains red balls, or that I draw something round. Well, those events are not mutually exclusive, right? They can happen at the same time. Something can be both red and round. There's nothing crazy about that. Now, if it were red or blue, and we had an urn filled with balls that were red and blue, then if we drew a red one, that would exclude the possibility of drawing a blue one. And if we drew a blue one, that would exclude the possibility of drawing a red one. And so we would say in that case that we should apply the restricted disjunction rule. So you have to really think about the events and think about the logic of the events. Are they consistent with each other? Can they happen together? If they can happen together, then you need to apply the general disjunction rule. If they cannot happen together, then you need to apply the restricted disjunction rule. So just to labor on it a little bit, if we look at different examples that deal with mutual exclusivity, we can probably get a better sense of what's going on here. So two events are mutually exclusive if the occurrence of one prevents the occurrence of the other. Let's say you flip a coin, you get heads, that excludes the possibility of getting tails. So those events are mutually exclusive. Now consider this other example. The contents of an urn contain 100 objects, 50 are spheres, 50 are cubes. And we say, suppose we randomly draw one object from the urn. What is the probability that the object is red or a cube? Well, we know, given the composition of the urn, that there are 50 spheres, 50 cubes, and each of the spheres and cubes, and of those populations, there are 25 of each that are red and blue, that it's possible for something to be both red and a cube. And so we need to be able to deploy the general disjunction rule as a way of calculating the probability of that event. And so here's the way it might work, right? So we have the R, where that's drawing something red, and C, that we're going to call drawing a cube. Something can be both red and a cube, so we just need to use the general disjunction rule. Sorry about that typo. And we would say the probability of being a red or a cube is equal to the probability of being red plus the probability of being cube minus the overlap of the probability of being red and a cube. Because remember, again, we're already adding together both of those categories, and those categories overlap already. So to avoid counting them twice, we have to subtract the overlap. So in this case, then we would have they're 50% red, 50% cubes, and then we subtract 0.25, and that equals, because that's the probability of being red and a cube. Note that you can apply the conjunction rule here to multiply them together, 0.5 times 0.5, and that'll give you 0.25, which will give us 0.75. Okay, so that's the general idea behind the disjunction rule. Again, the key to figuring out when you should use one or the other is to identify when a set of pair of events are, or I guess we'll usually be talking in terms of pairs of events, but this could extend beyond just simple pairs of events. But it's to determine when those pairs of events are mutually exclusive or not. Okay, so here's where things are going to get a little bit dicey. We're going to look at the definition of conditional probability. And then what I'm going to do is I'm going to motivate the use, I'm going to show you how you can use the rules that we have for probability so far to justify a rule for thinking about how inductive inference works. And then next week, we're going to apply that rule of deductive inference to different examples to show how you can perform calculations using that rule of inductive inference. The first step to understanding what it is that we're going to use, that if you've looked at the later slides, then you'll see the thing called Bayes' theorem. That's what I'm going to go through with you today, is the definition of conditional probability. So you'll recall that we have that vertical bar that can connect the variables, and that has a specific definition in the theory of probability. The probability of A if B is equal to the probability of A and B divided by the probability of B. So what we want to be able to say, we can apply this to certain different kinds of examples. So for example, if let's take this urn situation. We have 100 objects, 50 are spheres, 50 are cubes, just like the last problem I applied with disjunction. And we have another urn that has 100 objects, 30 are spheres and 70 are cubes. And notice that this is a slightly different distribution, but it's still 50-50. What is the probability of drawing something red or a cube if you draw it from urn A, right? And so notice the way this question is phrased. The probability of drawing something red or a cube if you draw it from urn A conditionalizes those events to drawing things from urn A. And so if you want to know what the probability, if we want to know what the probability of A or C is given B, right, then we would have to, then we could apply the conditional probability rule to get that result. And then the same thing would have to happen here, but we would conditionalize on urn B. And by the way, when I say conditionalize, I mean setting the condition on the right-hand side of that vertical bar. This B here, for example, on the right-hand side of the bar is the condition that we're setting. So we're conditionalizing when we say A if B, we're conditionalizing on B. But anyway, so, if you look at the answer, we would get different outcomes in each case. The probability of R or C of red or cube, if we draw from urn A, would be 0.75, just like the answer that we got from last time in the disjunction problem. The probability of R or C if B, notice that we used A and B here for urn A and urn B respectively, would be 0.85. So we get slightly different probabilities in these cases, and it has a lot of this has to do with the differences in the way that these are set up, because notice these are 50-50 each, but these differ a little bit, and so the probabilities will change a little bit depending on that, based on that. But I encourage you to go through the problem and work it through yourself. Realize that when you're dealing with the conditional probability, notice that it's defined already in terms of conjunction, and so you can just swap in the restricted conjunction rule to multiply the probabilities here to address that. And otherwise it's just division, right? So conditional probability is important from the standpoint of induction. So this is where I'm going to pull up a Word document shortly. But the idea here is that, think about it this way. When we're trying to defend the conclusion of an inductive argument, a part of what we're doing is we're saying that we're trying to ask the question of how probable it is that the conclusion is true if the evidence is true, or if the premises are true. And so this is where we're going to transition into talking from talking about events into talking about statements. But conditional probability helps to give us a first pass at understanding how it is that you might try to represent our inductive practices. What I mean by that is how we reason from evidence to conclusions using induction. And so what I'm going to do is I'm going to show you how, okay, or how we can get to a fuller picture of how it works. And so it's going to take a little work. You should really pay attention to the details as I go through this, but it's going to involve a very, very small and fairly straightforward mathematical proof. And so what the result will be what we call Bayes' theorem. Okay, so the main thing is to realize that's going on here as far as the background conceptual stuff is that realize that what we're trying to do with probability is, at least with respect to the course and the way I'm instructing you, is that we're trying to show how it is that we should adjust what we believe in light of the evidence that we're presented with. And so one answer that philosophers have offered up for how it is that we should understand what it means to have a rational belief is that your belief, all of your beliefs, should be consistent with the rules of probability. And as it turns out, people oftentimes stray from this. So I'm not going to get into the details here, but there's some famous psychological experiments that show that very often we don't obey the rules of probability when we're thinking about what we believe. So if you're at all curious about these kinds of cases, look up Linda the bank teller. Those experiments show that we violate the conjunction rules a lot, and even experts sometimes violate the conjunction rules when they're thinking about that. There's another mistake we make, which will become more apparent as I show you Bayes' theorem, where we ignore base rates. And so I'll get into what a base rate is when we get into Bayes' theorem. But the basic idea is that we neglect background information when we're thinking about the probabilities of events. And that'll become more apparent once we get into Bayes' theorem, sort of what is the information, the background information that we're ignoring. Okay, so anyway, so let's go ahead. I'm going to go ahead and back out of this. And so I'm going to show you how we would prove Bayes' theorem. And then we'll get into what Bayes' theorem is. Okay, so we start off with this definition of conditional probability, right? I'm not going to put the other rules up, but realize that the other rules are in the background and they're kind of important to have around too. So main thing is that we're actually not interested in just generic A's and B's when it comes to thinking about induction. We're interested in premises and conclusions. We're interested in evidence and hypotheses, right? And so what I'm going to do is I'm going to put things in terms of evidence and hypotheses. The evidence, I hope this is intuitive, will be our premises. The hypothesis will be our conclusion. And so I'm going to use H and E for that respectively. And so what we're going to do is we're going to change this around a little bit. Oops. Okay, so the probability of a hypothesis or a conclusion given its premises or evidence is equal to the probability of the conjunction of the hypothesis and the evidence divided by the probability of the evidence. So realize I just took these letters and said, hey, interpret them this way and then plug them into this formula. Okay, so don't think too hard about this. The reason I'm doing it is because recall what we're doing is we're trying to come up with the procedure for thinking about how our premises bear on our conclusions and inductive arguments in a way that's mathematically precise. So similarly, if we wanted to know the probability of the evidence given the hypothesis, we would say this. The probability of E of the evidence, if we assume the hypothesis, the probability of, say, there being rumbling in my attic, if I hear gremlin, if there are gremlins bowling in my attic, is equal to the probability of the conjunction of the evidence and the hypothesis divided by the probability of the hypothesis. Okay, so those are the two rules that we can apply here. Those are the two definitions of conditional probability. And what I'm going to show you is that if you assume these two definitions of conditional probability, we can derive Bayes' theorem, which provides us with a way of modeling how we should think about inductive reasoning. So the first thing to note is that one thing to do is we can actually show that these two are equivalent to each other. And to do that, it's pretty straightforward. You might remember this from some basic algebra, right? Multiply each side by the denominator of each of the fractions, right? So in this case, then we would end up with, let's just go ahead and copy and paste. We would end up with this. Okay, and then we can do the same here. So this shows that that the two right-hand on the right-hand side of the equals, that those two formulas are equivalent to each other. Why? Well, with the and relationship, you can kind of swap things around however you want. E and H is the same thing as H and E. So in this case, and if you want a more intuitive way of describing it that's more familiar to you, think about multiplying 2 times 3 and multiplying 3 times 2, because the conjunction here is equivalent to the simple multiplication problem, right? So we take the probability of H and E is equal to the probability of H times the probability of E, assuming that they're independent. So in that case, then this would be like saying the probability of 2 times 3 is 6, right? Well, the probability of 3 times 2 is 6 as well. It doesn't matter how you swap things around in the multiplication problem, you still get the same result. But these are equivalent to each other now, then. So this establishes that. And so what we end up with is that we can say that these, actually we're going to put this here, these are equivalent to each other, okay? So because these are the same, we can say that these are equal to each other. And if you want a mathematical justification for that, it's because of transitivity. So realize that transitivity is working in the background here. Okay, so now what we have is, this is pretty much gibberish. I mean, at least it's not complete gibberish, but it doesn't mean anything for what we need it for. But the interesting thing that happens is that we end up in a position where we can actually prove a very simple version of Bayes' theorem. And the way to do it is, again, to apply some very, very basic and simple algebra. And the idea here is, again, just to, you just take this entire thing, or here, we'll set it apart, that way you can kind of see how this works. So we'll just take, we'll divide each side by the probability of E. Oops, I don't know why I did that. Make sure we know that the entire thing is being placed over E, right? So here's what we get. If we want to know how much support some evidence provides for a hypothesis, then what we need to be able to do is find the probability of the hypothesis multiplied by the probability of the evidence given the hypothesis divided by the probability of the evidence. Okay, so that in a nutshell is what we call Bayes' theorem. And so notice that this almost follows straightforwardly from the way that we think about conditional probability. There are some other rules operating in the background. For example, the conjunction and multiplication rules are there in the background. But there you have it. That's Bayes' theorem. Now, there is one more step to get to the more accurate version of Bayes' theorem that we're going to need. And it involves using another rule of probability that I have not gone over with you all. And I'll mention it here, but it's not extraordinarily important that you understand it in its full, in the full level of depth that, say, like you might need to at a more, and for more sophisticated kinds of applications. But the basic rule is called the theorem of total probability. And what it says is that the probability of a piece of evidence, that's annoying, is equal to the probability of the evidence given the hypothesis plus the probability of the evidence given the opposite of the hypothesis, or the negation of the hypothesis. So recall that symbol, the negation that we used. So this rule basically just says that the probability of E is just the probability of E given every possible hypothesis that might bear on E. And so what we do is we take the massive disjunction of all of these, right? So you could actually just go through and say between all the like the probability of the evidence given this hypothesis or this hypothesis or this hypothesis or this hypothesis. But for our purposes, since we're doing some basic mathematics with this, we'll just throw in the plus, and we will say that the probability of the evidence is equal to the probability of the evidence given the hypothesis plus the probability of the evidence given the opposite of the hypothesis. So that's the theorem of total probability. Given that theorem, then we can complete our proof of Bayes' theorem, and it will look like this. Since we know probability of E is equal to that, you'll just have to take my word for it. We just plug in this on the bottom, right? And so what we have is in effect, the full version of Bayes' theorem. So this is not easy reading, but let's go through it slowly. It says the probability of the hypothesis given the evidence is equal to the probability of the hypothesis itself. That is what we call this in logic and in philosophy is our prior. That is what we believed, how probable we thought the hypothesis was before the evidence was introduced. Then the likelihood, the probability that the evidence would be there if the hypothesis were true, divided by the probability of E, or the probability of E given every single possible hypothesis that there is. In this case, we're always going to assume two hypotheses, one hypothesis and then its negation. So that's the general picture here. This is Bayes' theorem, and we just proved it. I know that was probably a bit of mental torture for you, especially those of you who aren't very mathematically inclined. But you know, I'll put you'll have access to this in the slides. In fact, I'll pull them up right now and show you. The basic idea is, though, that it captures the structure of inductive reasoning by showing us what information we have to be able to hunt down to show how much a piece of evidence will support a hypothesis. And again, this depends on these pieces of information. The probability of the evidence, if we assume the hypothesis, the probability of the hypothesis itself, and then this weighted function here of all of the possible hypotheses that might bear on the problem. And actually, I just noticed an error that I'm going to go ahead and correct real quick. So this should be the So this should be the probability of H, and then the probability of not H. Yeah. So the idea here ends up being that we weight every single, we look at the products of all of the hypothesis and the probability of the evidence given the hypothesis. So a couple of things to note about Bayes' theorem. So first is that the top part of the numerator always matches the left-hand side of the denominator. So if you're thinking about how to unpack these things later, the probability of E given H and the probability of H, this left-hand side is always going to map onto the top part here. But the really important thing, the mathematical details are important, but I think a little less important than what we're going to apply it to is that this provides us with what information we need, again, to know how much our premises support our conclusion, right? So we say, how probable is our conclusion if we assume our premises, or hypothesis if we assume our evidence? And that's the important point here, that this captures the mathematical structure of good inductive reasoning. And there are a ton of properties you can show about how we can expect, given different priors, how we can expect new pieces of evidence to influence the probability that gets pumped out of filling in all these variables. But we'll get to some of that. We won't get to all of it. But this is the basic structure of it. And for your purposes, other than kind of getting a sense of how that proof worked, you should get a sense of what all of these terms mean. And so what all these key terms are, the bolded terms here. And to sort of understand the general structure of this, it's going to make your life a lot easier once we get to the later quizzes, once you get to the last quiz, anyway, later quizzes. So once you get to the last quiz, a lot of the pressure will be placed on getting you to unpack and understand inductive arguments that are occurring, and using Bayes' theorem to unpack those inductive arguments. So as a final note, I mentioned base rates earlier, and the base rate that, as far as the definition of all, as far as the definition of it is concerned, is just this piece of information here, the prior probability that the hypothesis is true. And so what we're looking for is just kind of like the information in the background that is helping to inform how that evidence is going to bear on the truth of the hypothesis. And a part of that is just how confident, how much we already believe, rather, the hypothesis in question. Okay, so get ready for quiz 10. That will be coming up soon. Quiz 9 will cover mostly disjunction rule stuff, and I might ask you a couple of questions about Bayes' theorem and to explain like sort of what's going on in the case of Bayes' theorem. I won't ask you for like the proof or anything like that, though. Like I think it helps your understanding if you try to understand what led to the proof, and then how to interpret the proof. And that's something I really want to stress, that, you know, this sounds kind of, I think I'm going to sound something that sounds a bit like a platitude, but you know, like the mathematics, they're just symbols. What makes them interesting is how we interpret them. And so there's no reason that this particular equation needs to be understood as a piece of as a way of modeling induction, but somebody saw that you could interpret it that way and showed how you could layer on that interpretation on top of the symbolism to get the right results. And so realize that what we're trying to do here is not so much become masters of mathematics, but to understand the conceptual underpinnings for how this could represent inductive reasoning. That does involve doing a bit of mathematics, so you'll have to calculate some probabilities using this formula. But again, the basic idea is not to do very sophisticated math. It's to get a sense of how this manages to capture the structure of our inductive reasoning. Okay, so that's what I have for you today. Please direct any questions my way and let me know when you're ready for the next quiz. And, you know, we're almost done. You're almost there. So, yeah, take it easy.